I know I'm fashionably late, but let me extend to you all my very best wishes for the new year 2026. So, I was watching YouTube videos from other maths YouTubers looking for a different angle, or something that hadn't been done before. That's when I felt slightly ticked off by a YouTube comment. I know, right? What a surprise. Well, at least I had found the topic of my next video. Let's get started with numbers. I would hazard a guess that many, if not most of us, feel quite comfortable with whole numbers and integers. So do I. They're just very intuitive, familiar. I trust I don't really need to explain why. The rational numbers are fairly approachable as well, since at the end of the day, it's just a matter of dealing with two integers at the same time, right? It gets a little confusing with things like 4/6 being the same as 2/3, but that's manageable. There is, however, a terrifying monster lurking in the machinery. What was that? Anyway, these are the places I like to explore the most. The reals, on the other hand, are quite intimidating, at least to me. The uncountable infinity, the strangeness of the rationals having density 0 in that space, it all feels vast and deep. It's the same feeling I had the first time I stood in front of the Pacific Ocean. One cannot help but feel very, very small in such moments. And the complex numbers? The square root of -1, you said? Of course, we all know it makes absolute sense, and it's beautiful on so many accounts. But to tell you the truth, when I think in terms of complex numbers, I feel like the first time I saw Carl Sagan's pale blue dot. Not just small, but utterly, soul-crushingly insignificant. In between these extremes, there are other subsets of numbers. By the way, if you're looking for a more exhaustive map of this territory, I highly recommend the Numberphile video featuring Matt Parker. I've linked that in the description. The first subset to mention is the set of algebraic numbers. Those are all the numbers that are solutions to polynomials of arbitrary degree with rational coefficients. And then, the numbers I'd like to talk about today, the constructibles. In other words, the rationals combined with the square roots. So, why do I feel okay with square roots? Well, I think it's because I learned that we can write them like this. See, it's just whole numbers, listed and arranged in a very particular way. As you probably already know, this is called a continued fraction, and this notation is simply a shorthand for this infinite staircase thing. The biggest advantage of this representation is that it makes the difference between rational numbers and irrational ones crystal clear. The continued fraction expansion of a rational number is always finite. It stops. But for irrational numbers, like the square root of 2, this expansion goes on forever. Moreover, the expansion of square roots has this beautiful additional feature. It always ends up repeating itself periodically. A very famous example of continued fractions is this guy. I'm sure you've seen it in many videos, and it's commonly described as being the most irrational number. It's an old memory, but I vividly recall my high school teacher doing the derivation on the blackboard. First, he pointed out that this block is the exact same thing as the entire right-hand side, which meant that he could replace that first block with x. Now, all he needed was a few steps of algebraic manipulation to arrive at a simple quadratic equation. And you all know the solution. It's phi, better known as the golden ratio. I can't resist the temptation of reliving a little moment of glory I had in that classroom a little while later. The teacher wrote this on the board and asked if one of us could find x. After a couple of seconds, I had a sudden idea. It must have shown on my face, because the teacher almost immediately called me up to the board. I started by writing out the staircase version of the equation. My idea was to try the same kind of trick we had used for the golden ratio. The best way I could think to do it was to add 7 to both sides. Then, I was allowed to replace this bottom part with x plus 7. From there, it was smooth sailing. Until I arrived at the final result. X equals the square root of 56. Thank you for indulging me while I walk down memory lane. I promise I won't do it too often. But there's something else about continued fractions that I discovered much later. Something I've never actually seen discussed anywhere. Not in that classroom of my past, and not in any video or online resource. Being able to write things down simply is nice, but a visualization is even better. I'm going to show you how to calculate the continued fraction expansion of phi geometrically. Take a rectangle with side lengths of 1 and the number you want an expansion for. Now the question is, what is the largest square you can fit in the empty space? And specifically, how many of those can you fit? That's right, just one. We have the first number in our expansion. Now we just repeat. What's the largest square fitting in the remaining space? And how many do we need? Yep, one again. And we just keep going. Of course, I have to draw the famous spiral. In fact, this exact same procedure applies to all numbers. Let's take Euler's number. Its continued fraction expansion is well known, and as you can see, the geometric intuition fits perfectly with the numerical result. Let's now take a look at the square root of 2. And one last example. Let's see the square root of 3. Looking at these spirals, it's obvious that they all converge. This reminded me of the visual of the Riemann zeta function as depicted in that 3 blue 1 brown video about the Riemann hypothesis. So, I was curious and I produced this picture. That's not really a fractal, by the way. Under those fat pixels, there could be any number of points of convergence for these expansions. In fact, I'm quite unsure how to dig deeper with this, so I'm going to leave it unresearched for now. Maybe I'll find some time another day. Coming back to the geometric interpretation with the rectangle and the sequence of squares, I have often wondered whether the Pythagoreans would have accepted irrational numbers as infinite rationals. Wait, that sounded almost philosophical for a second. Infinite rationality produces irrationality. Never mind. Since we're now way back in the past, let's briefly travel through the centuries. Euclid didn't deal in continued fractions, of course, but the algorithm for the greatest common divisor included in the elements has a modern version that generates a continued fraction as the sequence of quotients of successive Euclidean divisions. I'm not aware that John Wallis obtained particularly groundbreaking results while working with continued fractions, but he has to be credited as being the first to actually coin the phrase. He's also famous for inventing the symbol for a familiar nightmare, infinity. But that's for another video. Moving on. Euler proved that his own constant, E, is irrational by using continued fractions. Well, he needed more than just that, but they were certainly key to the success. Lambert achieved a similar result with pi, proving its irrationality using continued fractions as well. Then there's Lagrange. Just 2 years after providing a general solution to Pell's equation, again using continued fractions, he proved that quadratic irrationals have periodic continued fraction expansions. We'll leave the timeline here. I think the point is quite obvious. Continued fractions have been a remarkably sharp tool in many groundbreaking proofs throughout history. Mind you, I'm omitting and most likely missing many other related results. I'd like, however, to talk about 2 more recent applications before we conclude. Closer to us, I should mention this 1924 seminar paper by Emil Artin. To be honest, I'd never have heard of, much less understood, any of that paper, if not for the wonderful depiction Caroline Series made of it in the early 80s. That article is a wonderful read that I highly recommend. Think of her as a 3 blue 1 brown of her time. The exposition is clear, patient, and engaging. It's truly delightful. It makes you feel like you're actually smart enough to follow all the intricacies. It's just amazing. Coming back to our topic, I'll quote Caroline. The content of this paper, meaning Artin's, is that the behavior of certain curves on a particular Riemann surface can be understood by the use of elementary results from number theory about continued fractions. This is the Erdős-Mosher equation. Only one trivial solution is known, and Paul Erdős conjectured in the 50s that there are no other solutions. In 2011, it was shown that 2k over 2m minus 3 must be a convergent of the natural log of 2. Another piece of jargon. A convergent is just a truncation of an infinite continued fraction. Essentially, it's a rational approximation of the irrational value in question. Right now, this problem is still open, but it could very well be that this continued fraction fact represents a key factor in the final solution. And finally, coming back to where it all started. Dear Mr. YouTube commentator, some things are called elementary in mathematics, but as it turns out, they are anything but. So, no, continued fractions are neither antiquated nor useless. Have a good one, guys, and see you around.